Hello all. Today we are going to discuss about periodic noise. Periodic noise is one such a disruption that has a periodic pattern in the spatial domain, causing hills in the image spectrum. In practice, quasi-periodic noise is commonly encountered instead of periodic noise. Periodic noise has a global impact in spatial domain and can only be removed using frequency domain analysis. In this paper or in this chapter, a novel frequency domain technique is proposed for the removal of semi-periodic and quasi-periodic noise for both grayscale image and color image. Periodic image is an image arises typically from electrical or electromechanical interference during image acquisition. This is only a type of spatially dependent noise that will be considered in this chapter. Then next topic is estimation of noise parameter. The noise parameters are estimated by using the selected weak texture patches from a single noisy image. Experiments on synthetic noisy image are conducted to test the algorithm, which show that our noise parameter estimation outperforms the existing algorithms. The parameters of periodic noise typically are estimated by inspection of the Fourier spectrum of the image. Periodic noise tends to produce the frequency spikes that often can be detected even by visible analysis. Another approach is to attempt to infer the periodicity of the noise components directly from the image, but this is possible only in the simplistic cases. The figure represents estimation of noise parameter. Consider the image. This image is severely corrupted by the sinusoidal noise of the various frequency. The Fourier transform of the pure sinusoidal is a pair of conjugate impulses located at the conjugate frequency of the sine wave. Thus, if the amplitude of the sine wave in the spatial domain is strong enough, we would expect to see in the spectrum of the image a pair of impulses for each sine wave in the image. As shown in figure B, this is indeed the case with the impulse appearing in an approximate circle because the frequencies value in this particular case are so arranged. We will have much more about these and other examples of periodic noise. The simplest use of the data from the image strip is for calculating the mean and variance of intensity levels. Consider a strip denoted by S and let PS of Zi is equal to 0, 1, 2 up to L minus 1 denote probability estimates of the intensity of the pixel in S, where L is the number of possible intensity in the entire image. We estimate the mean and the variance of a pixel in S as follows. Z bar is equal to summation of I is equal to 0 to L minus 1 Zi PS of Zi sigma square is equal to summation of I is equal to 0 to L minus 1 Zi minus Z bar bracket square PS of Zi. The shape of the histogram identifies the closest PDF match. If the slope is approximately Gaussian, then the mean and variance are all we need because the Gaussian PDF is completely specified by these two parameters. Let us consider the example. The vertical strip of 150 by 20 pixel shown in figure were cropped from the Gaussian railing and uniform images from last figure. The histogram shown were calculated using the image data from these small strips. The histogram that correspond to the histogram in the image are the ones in the middle of the group of 3 in. We see that the shape of this histogram correspond to the quite closely to the shapes of the histogram in this figure. The height of the different due to scaling, but the shape are unmistakably similar. Then next topic is restoration in the presence of noise only spatial. When the only degradation present in an image is noise, then it becomes g of x is equal to f of x plus y plus eta x of xy. G of uv is equal to f of uv plus n of uv. The noise terms are unknown, so subtracting them from g of x comma y or g of u comma v is not a realistic option. In the case of periodic noise, it usually is possible to estimate n of u comma v from the spectrum of g of u comma v. In this case, n of u comma v can be subtracted from g of u comma v to obtain an estimate of the original image. In general, however, this type of knowledge is the exception rather than the rule. Spatial filtering is the method of choice in situations when only additive random noise is present. Spatial filtering, with the exception of the nature of the computation performed by the specific filter. The mechanism for implementing all the filters are exactly same. Then next topic is mean filters. Mean filtering is a simple, intuitive and easy to implement method of smoothing images, that is reducing the amount of intensity variations between the one pixel and the next. It is often used to reduce noise in images. First type is arithmetic mean filter. The arithmetic mean filter is defined as a average of all the pixels within a local region of an image. Pixels that are included in the averaging operation are specified by the mask. This is the simplest of the mean filter. Let S of x comma y represent the set of coordinates in a rectangular sum-image window of size m by n, centered at a point x comma y. The arithmetic mean filter computes the average value of all the corrupted image g of x y in the area defined by S of x comma y. The value of restored image f cap at a point x comma y is simply the arithmetic mean computed using the pixel in the region defined by S of x comma y is given by f bar x comma y is equal to 1 upon mn. A summation of S of t implies S of x comma y g of st. This operation can be implemented using a spatial filter of a size m by n in which all the coefficients have value 1 upon mn. A mean filter smooths local variation in an image and noise is reduced as a result of blurring. Then next type is geometric mean filter. An image restored using a geometric mean filter is given by the expression f cap xy is equal to summation of S of t implies S of xy g of st raised to 1 upon n. Here, each restored pixel is given by the product of the pixel in the sub-image window raised to the power of 1 upon mn. A geometric mean filter achieves smoothing comparable to the arithmetic mean filter, but it tends to lose less image detail in the process. Next type is harmonic mean filter. The harmonic mean filtering operation is given by the expression f cap xy is equal to mn upon summation of S of t implies S of xy 1 upon g of st. The harmonic mean filter works well for salt noise but fails for paper noise. It does well also with the other type of noise like Gaussian noise. Then next is the contra-harmonic mean filter. The contra-harmonic mean filter yields a restored image based on the expression f cap xy is equal to summation of s comma t implies S of xy g of s comma t q raised q of q plus 1 upon summation of s comma t implies sx g of st q, where q is called as a order of the filter. This filter is well suited for reducing or virtually eliminating the effect of salt paper noise. For the positive values of q, the filter eliminates paper noise. For the negative value of q, it eliminates salt noise, but it cannot be both simultaneously. The contra-harmonic filter reduces the arithmetic mean filter if q is equal to 0 and to the harmonic mean filter if q is equal to -1. This figure shows an 8-bit X-ray image of a circuit board, and figure B shows the same image but corrupted with the additive Gaussian noise of a 0 mean and variance of 400. For this type of image, this is significant level of noise. Figure C and D show respectively the result of filtering the noisy image with an arithmetic mean filter of a size 3 by 3 and a geometric mean filter of the same size. Although both the filter did a reasonable job of attenuating the contribution due to a noise. The geometric mean filter does not blur the image as much as arithmetic filter. For the instance, the connector fingers at the top of the image are sharper in the figure D and in C. The same is true in the other parts of image. This figure A shows the same circuit image but corrupted now by paper noise with the probability of 0.1. Similarly, the figure B shows the image corrupted by salt noise with the same probability. Figure C shows the result of filtering figure A using a contraharmonic mean filter with Q is equal to 1.5, and figure D shows the result of filtering figure B with the Q is equal to minus 1.5. Both the filter did a good job in reducing the effect of the noise. The positive order filter did a better job of clearing the background at the expense of slightly thinning and blurring the dark areas. The opposite was true of the negative order filter. In general, the arithmetic and the geometric mean filters are well suited for random noise like Gaussian or uniform noise. The contraharmonic filter is well suited for impulse noise, but it has the disadvantage that it must be known whether the noise is dark or light in order to select the proper sign for Q. Next topic is order statistic filter. Order statistic filter are a non-linear spatial filter whose response is based on the ordering or ranking of the pixels contained in the image area encompassed by the filter, and then replacing the values in the center pixel with the value determined by the ranking result. Then next type is median filter. The median filter is a non-linear digital filtering technique often used to remove noise from an image or signal. Such noise reduction is a typically pre-processing step to improve the result of later processing. For example, edge detection on an image. The best known order statistic filter is the median filter, which as its name implies replace the value of pixel by a median of intensity levels in the neighborhood of that pixel. F cap xy is equal to median S of t implies sxy g of st. The value of the pixel at x, y is included in the computation of the media. Median filters are quite popular because for the certain type of random noise, they provide excellent noise reduction capability with a considerably less blurring than the linear smoothing filter of similar size. Median filters are particularly effective in the presence of both bipolar and unipolar impulse noise. Next type of filter is maximum and minimum filter. The minimum filter is defined as the minimum of all the pixels within a local region of an image. The minimum filter is typically applied to an image to remove positive outlier noise. The maximum filter is defined as the maximum of all the pixels within a local region of an image. The maximum filter is typically applied to an image to remove negative outlier noise. Although the median filter is by far the order statistic filter most used in image processing, it is by no means the only one. The median represents the 15th percentile of the rank set of number. For example, using 100 percentile result in the so-called max filter is given by f cap xy is equal to maximum h comma t implies s of xy g of s comma t. This filter is useful for finding the brightness point in an image. Also, because paper noise has a very low values, it is reduced by the filter as a result of the maximum selection process in some image area Sx. The zeroth filter is the minimum filter is given by f cap xy is equal to minimum s comma t implies sxy g of s comma t. This filter is useful for finding the darkest point in an image, and also it reduces salt noise as a result of a minimum operation. Next topic is midpoint filter. The midpoint filter is typically used to filter images containing short tail noise such as Gaussian and uniform type noise. The midpoint filter is defined as where the coordinate x plus I comma y plus j is defined over the image A and the coordinate I comma j is defined over the n by n psi square mask. The midpoint filter simply computes the midpoint between the maximum and minimum values in the area encompassed by the filter. F cap x comma y is equal to 1 by 2 maximum s of t implies sxy g of st plus minimum s comma t implies sxy g of s comma t. Note that this filter combines order statistic and averaging. It works best for randomly distributed noise like Gaussian or uniform noise. Next type of filter is alpha trimmer mean filter. Alpha trim mean filter is window filter of nonlinear class. By its nature is hybrid of the mean and median filter. The basic idea behind the filter is for any element of the signal, look at its neighborhood, discard the most atypical element and calculate the mean value using the rest of them. A filter is formed by the averaging these remaining pixels is called as a alpha trim mean filter. F cap xy is equal to 1 upon mn minus t summation of s comma t implies sxy g of s comma t, where the value d can be ranged from 0 to mn minus 1, where d is 0. The alpha trimmer filter reduces to the arithmetic mean filter. If we choose d is equal to mn minus 1, the filter becomes a median filter. For other values of d, the alpha trim filter is useful in a situation involving multiple type of noise such as combination of salt and pepper and Gaussian noise. In next lecture, we are discuss about remaining types of filter. Thank you guys.